So in today's session, I'll present two different types of problems which can be solved by using 3D approach. The first problem that I'm going to discuss is optimal merge patterns. So you already know what is two-way merging. Two-way merging is the basic step that is used in merge sort. So consider that I have two lists, list A and list B. Lists A and B are sorted lists. You can see that they are already sorted in ascending order. List A is sorted in ascending order. List B is also sorted in ascending order. Now I have two sorted lists which needs to be merged because I am merging two lists. This is called as two-way merging. I can go for merging of more number of lists, then that will be called as k-way merging, where k indicates the number of lists that are to be merged. Now I'm going to apply two-way merging method to merge these lists, and I'm going to form a third list, C, whose size will be equal to the size of A plus the size of B. So here A list is of size 5 and B list is of size 3. After merging, you are going to get another sorted list C whose size is 8. Now, starting the two-way merging process, I'll be needing 3 pointers. The first pointer will be pointing to the first element in first list. Second pointer to the beginning of the second list. Third pointer will be pointing to the beginning of the final list. Okay, A's pointer, B's pointer, and C's pointer. Now, these two pointers will be useful for making a merge operation. Now, the process will go like this. You are going to compare this element from A and this element with B, and whichever element is lesser, that I am going to copy it into the final list. So among 1 and 3, 1 is minimum. So I'm going to copy 1 here. Then I'm going to move the pointers and I'm going to repeat the process. Which pointers I have to move forward? I have to move forward this pointer. And I also have to move forward this pointer. This pointer has to be moved to the next element because 1 is now already copied. So 1 copying is already done. This element is over. So moving the pointers, I have moved the pointers to the next locations. Now again compare 3 with 5. So now you can understand what is the requirement for having pointers for comparing the elements from A list and B list. Now you are going to compare 3 with 5. The minimum element is 3. So I'm going to copy 3 here. I've copied 3 into the final list and I'm going to move the pointers forward. Which pointers I have to move forward? I have to move forward this pointer and this pointer because now 3 is copied. So 3 is copied. I'm going to move the pointers forward and now this process is going to be repeated. Now you have to compare 4 with 5. Copy 4, then move the pointers forward. Now compare 5 and 6. 5 is the minimum element. So copy 5 here, move the pointers forward. So then compare 6 and 7. 6, copy it here, move the pointers forward. Now compare 7 and 8. Copy 7 and then move forward. So now all the elements from the B list are completed copying. So I'm left out with only the elements from A list. So I'm going to directly copy the remaining elements from A list into the final list. Now you can see that I have got two sorted lists, A and B, and I have performed two-way merging, and I have got a single sorted list of size 8. This is what is called as two-way merging, where two sorted files are merged into one sorted file. And the time complexity of two-way merging, you have the first file of size n, the second file of size m, and you are going to combine these two lists to form a single list, and the complexity of merging is n plus m, big O of n plus m. The size of the first file plus the size of the second file, that will be the time complexity of merging these two files. Now you can apply the same procedure for performing k-way merging, where you are going to merge k number of files into a single sorted file. Now, if you have only two files and you want to perform two-way merging, then there will be only one solution. But you have more than two files, then you may directly apply k-way merging. Single k-way merging you can apply, and you can merge k files, or you can perform repeatedly two-way merging. So at a time, you are going to merge two files, and you are going to repeat the process until all k files are merged. Now, for this process, given k number of files, there will be many number of solutions depending upon how you are performing the merge operation. So I'm going to take an example here. The problem states that there are four sorted lists, L1, L2, L3, and L4. All these are sorted, and the size of each list is 30, 15, 10, and 20 respectively. And given four lists, you have to merge them into a single sorted file. Now you can directly apply four-way merging. At a time, you are going to merge all the four files into a single sorted file. But here the question is given that you need to merge using two-way merging. That is, at a time you can merge only two files. So if I go with these solutions, there are many solutions that are possible. This is one of the solutions. I'm representing here the merging process in the form of a binary tree. Binary tree because the merging type is two-way merging. So I can represent the two-way merging process in the form of a binary tree, and this is what is called as a binary merge tree. Representation of merging process in the form of a binary merge tree. So here this tree will have the leaf nodes. Each of this leaf node will represent the size of the list. This is the size of L1, size of L2, size of L3, size of L4. Now you need to merge all these files so that you can form a single sorted file. Now the constraint here is that you can merge only two files at a time. So I'll go with this process. I'll first merge list 1 and list 2. List 1 has 30 items, list 2 has 15 items. I want to merge. When I perform merging of these two files, I'll have a single sorted file, and the time complexity of this sorting is 45. That is the size of the first file plus the size of the second file, big O of n plus m, 45. Now, step 2, I'm going to merge list 3 and list 4. two-way merging I am going to apply. And the time complexity of merging L3 and L4 is 30. Size of L3 plus size of L4. Now I have merged 4 files using two-way merging and I have got 2 sorted files. Now I'll try to perform again two-way merging on these 2 sorted files. And the time complexity of merging will be 75, which is 45 plus 30. Now I have merged 4 lists into a single list and the number of comparisons will be 45 plus 30 plus 75. Total complexity of the entire merging process. This is first merging. This is second merging. This is third merging. So 3 merges I have performed. And the time complexity of first merge is 45, second merge operation is 30, third merge operation is 75. So the total complexity of merging 4 lists into a single list using two-way merging is 150. Now this is one solution that I have. One merge pattern. I can have many such patterns. This is another pattern that I can go for. This is a merge pattern. I have still the same 4 lists and I want to combine them into a single list. But now first I'm combining L1 and L3. Then I'm combining this result with, I'm combining L1 and L2. Then this I'm combining with L3. Then the result I'm merging with L4. And the time complexity is 175. Now I have another merge pattern here. I'm first merging L2 and L3. The result is further merged with L4. Then this result is again merged with L1. So first L2 and L3 are merged, then L4, then L1. This is another merge pattern with the time complexity of 145. Now, which is the optimal merge pattern? So the optimal merge pattern will be the one which will give you minimum number of comparisons. So among these 3, this can be considered as the optimal pattern because it's giving me the minimum number of comparisons. Now, how to identify which merge pattern is optimal? For that, you are going to apply greedy approach. So whenever you are going to merge any 2 lists, you are going to select the smallest sized lists. That is the optimization measure or the selection procedure for the optimal, for finding the optimal merge patterns. At any step, you want to merge any 2 lists, you are going to select those lists that are of smallest size. Now, I want to merge L1, L2, L3, L4. I want to select any 2 lists for merging. Then I'm going to select those lists which are of smallest size. So you see the size. This is L2 whose size is 15, L3 whose size is 10. So these 2 I'm going to select and I'm going to merge. Now I have this file whose size is 25. Then I have this file whose size is 30. This which size is 20. So I have 3 sorted files now. L1, L4 and the union of L2, L3. Now among these 3, if you want to further merge any 2 files, select those 2 files with minimum size. So I'm going to select this file and I'm going to select this file and I'm going to merge. Again, now you have 2 sorted lists. One is of size 45, another is L1 with size 30. Remaining only 2 files, so I'm going to merge them. So as such, at each step, if you are making a greedy choice, then you'll be able to determine an optimal merge pattern. Okay, so an optimal merge pattern is a merge pattern that allows merging of 2 or more sorted files into a single sorted file using two-way merging with minimum number of comparisons. There might be many merge patterns. There might be many merge patterns that are feasible, but the merge pattern that gives you minimum number of comparisons, minimum time complexity, that is called as optimal merge pattern. So for finding an optimal merge pattern, you are going to apply greedy approach. You are going to identify the optimization measure and the objective function for the given problem. The given problem is to determine the optimal merge pattern. So the objective function is to minimize the computing time. How computing time can be minimized? By minimizing the number of comparisons. Now, what is the optimization measure or the selection procedure that we have to apply? At each step of merging, you have to select the smallest sized files for merging. So this is your optimization measure and selection procedure. So at each step, you are making a greedy choice. And if you are making a greedy choice, then there is every possibility that your objective function will be satisfied. So this is your optimal merge pattern. Now, as I have already told, the merge patterns, two-way merge patterns, can be represented by using a binary merge tree. So I have already presented in the previous slides that the files themselves, the lists themselves, will be your leaf nodes. The value of each leaf node will be the size of the file. And then you'll merge. At each step, two files will be merged into a single file until at the root node, you'll get a single sorted file. So now, if you can see, this was the optimal merge pattern. And for this optimal merge pattern, I have computed the number of comparisons, or the time complexity of merging is 145. So for this, I have made a sum of the internal nodes. So these are the internal nodes, 25, 45, and 75. So I have added the weights of the internal nodes, 25 plus 45 plus 75, which is equal to 145. So the formula for this, for finding the merging cost, the formula is the sum of products of the number of records and its depth. Sum of products of the number of records in each file and its depth. So this can be calculated as, you can see, for each file there are 4 files. Now take this file, take this list L1, whose size is 30, into what is its depth? Depth from the root node. It is equal to 1. So that is 30 into 1. The size of the file into its depth in the tree, plus the size of list 2 into its depth in the tree. So list 2 size is 15. Its depth is the distance from the root node. So here you can see, from list 2, if you want to reach root node, you have to travel 1, 2, and then 3. So the distance from the root node to list L2 is 3. So it is 15 into 3. In the same way, for list L3, its size is 10 into its distance from root, 1, 2, and 3. 10 into 3, 30. Then finally list 4, its size is 20, and the distance from the root is 1 and 2. So finally I have got 145. So you can use any one of the formulas for calculating the merging cost. You can use the formula which is sum of the weights of the internal nodes, or you can use the formula which is mentioned here. And this tree is generally, now it's called as binary merge tree, but in general, it is called as weighted external path of tree. Weighted tree. It's generally called as weighted tree. Now this is the greedy algorithm for generating optimal merge patterns. So we have to maintain the data in the form of a binary tree. So you can see that each node in the tree has to maintain the weight. It has to maintain a pointer to the left child. It has to maintain a pointer to the right child. It's the general structure of a binary tree node. So each tree node will contain an integer weight. It will contain a pointer to the left child. It will contain a pointer to the right child. Now, this is the algorithm which generates an optimal merge tree. You are going to repeat the process for n-1 number of times. n-1 times. That is, if you can see the figure here, there are 4 lists. How many merges did we perform? We have performed 3 merges. First merge, second merge, and third merge. So if there are n number of lists, you'll have to perform n-1 number of merges. So this is the process for merging. Each time you are going to merge any 2 lists. So you are going to create a new node in the tree. Then you are going to find out the smallest sized list. So least method, which will give you the smallest sized list, which will become the left child. Next least sized list. Next second smallest sized list will become the right child. Now you are going to merge these 2. And the weight of the parent will be equal to weight of left child plus the weight of the right child. And you are going to insert this new parent node into the tree. And finally, after n-1 merges are performed, you are going to return the root node, the entire tree, which will be representing your optimal merge pattern. And the time complexity of this greedy algorithm, you have 2 cases. If the lists are maintained in non-decreasing order, then the time complexity will be big O of n square. Lists themselves are maintained in non-decreasing order. That means you can see the figure here. This is L1, L2, L3, L4. They are not maintained in any particular order. If I maintain the lists in the non-decreasing order, that means 30, 20, 15, and 10. In the non-decreasing order, if the lists are maintained, then the time complexity of this greedy algorithm is big O of n square. If the list is represented as a heap, a min heap, the lists are represented in the form of a min heap, then the time complexity of this greedy algorithm will be n log n. So that was optimal merge patterns solved using greedy approach. Further, we'll see Huffman codes. So we'll start with what is the necessity of Huffman code and how it increases the efficiency of data transmission or data storage. Assume that there is a message available which has n number of characters that need to be transmitted or that needs to be stored on your hard drive. So assume that this is the message. A message will be consisting of n number of characters. Either this message has to be transmitted on a computer network or it might have to be stored on a hard disk. In general, whenever a message has to be transmitted or it is to be stored, then each character is stored in the form of an 8-bit ASCII code. This is the international standard code that is used to represent n characters, and each ASCII code will be of 8 bits. Now, say for example, I have a message of 10 characters, or consider this message whose length is 15. It has 15 characters. Now, if I have to encode these 15 characters using 8-bit ASCII code, each character has to be represented using an 8-bit ASCII code. As such, 15 characters each will be represented using 8 bits. Totally, if you want to transmit this message on the network or you want to store this message on the hard drive, it will require 120 bits of space. Now, using 8-bit ASCII code, totally 256 different characters can be represented. But considering only your message that is being transmitted, it may not contain all 256 characters. You can see that in this particular message, only 2 characters are being used, capital A and capital B. Not entirely all the 256 different characters are not being used. So these 256 different characters will contain lowercase alphabets, uppercase alphabets, digits, symbols like plus, minus, control characters like control, shift, alt, and so on. All the 256 characters, you might not be using them in your message. Then, how can I reduce the total number of bits being transmitted if you are not using all the 256 characters? Then for that, instead of using the ASCII code for encoding, you are going to prepare your own encoding scheme. Customized encoding scheme you are going to develop for yourself. Now, there are 2 types of encoding schemes. The first one is called as fixed length encoding. So assume that this is your message whose length is 15 characters, but only 2 different types of characters are being used in the message, and the characters are A and B. Now, I'm going to develop my own encoding scheme. I'm not going to use ASCII code. So if I have to give a unique code for each character, there are only 2 characters, then a single bit code will be sufficient. 1 bit code will be sufficient. So for that, whenever you have to represent character A in the form of zeros and ones, A will be represented as a single 0, B will be represented as a single 1. That means whenever using this particular scheme, a message has to be encoded, then it will look like this. A will be represented using a 0, B will be represented by using a 1. So this will be your encoded message. Now, how many bits did it take? The encoded message, how many bits it take? It took only 15 bits. Right? Because each character is represented by using only 1 bit code. Now, how you are going to calculate that? You are going to calculate that using a formula which will require you what is the code, size of the code, and what is the frequency of the characters. What is the code for character A? What is the size of the code? It's 1 bit. How many times A is repeating in your message? In your message, how many times A is being repeated? 9 times. Now, B character is repeated for 6 times. Now, 15 bits is the length of the encoded message. 15, how did I get it? It's 9 into 1 plus 6 into 1. That is the frequency of A into its code length. frequency of A into its code length. The code length is 1, number of bits used in the code. Then frequency of B into its code length, which is again 1. So you have got 15 bits. So you have used the formula. Now, is it sufficient if I send only this encoded message on the network? No, it will not be sufficient, because I have made this encoding scheme myself. It's my own encoding scheme, not the standard encoding scheme. If I use the standard ASCII code for encoding, on the sender side, encoding will be done using ASCII code. On the receiver side, decoding will also be done using the same ASCII code. So both sides know what is ASCII code. Both the sender and receiver already know what is an ASCII code. ASCII code is international standard. So both the sides, they know ASCII code. So encoding can be done and decoding can also be done. But now here, this is my own encoding scheme. The receiver does not know how I have encoded. I have here represented A with a 0, B with a 1. How come the receiver knows how character A is represented, how character B is represented? So for that, along with this message, encoded message, I have to also send this encoding table. Encoding table will consist of what is the character and what is its code. This 2 columns, the character and the code, it's called as encoding table. This also needs to be sent along with the message. So the message plus encoding table also needs to be sent to the receiver. Now, this is 15 bits size. And now what is the size of this encoder table? So this is your encoder table. Now what is the size of this encoder table? That will be representation of A in ASCII code, representation of B in ASCII code. Here we are going to use standard ASCII code. So for representing A and B using ASCII code, it will take 16 bits. And what is the code for A? It is a single 0. What is the code for B? It's a single 1. 2 bits. So 16 plus 2, encoding table size will be 18 bits. Now, what is the total length of transmission? It's the length of the encoding table plus the length of the original encoded message, which is 18 plus 15, 33 bits. Now, if you are making your own customized encoding scheme, then this message, if it has to be transmitted over the network, then you'll have to transmit 33 bits, which is far better than 120 bits, because if you have transmitted this message using 8-bit ASCII code, then the transmission size would have been 120 bits. But instead, you are transmitting only 33 bits. That is very less transmission size. So that will be the advantage of having your own encoding scheme, but both the sender and the receiver should have the same encoding table. Then only you can encode or you can decode. So this is fixed length encoding scheme. Instead, you can have a variable length encoding scheme, which is supported by Huffman coding. So Huffman coding is compression technique that is used for reducing the size of the messages. And it provides you with variable length encoding. Now this is your problem. The given problem is you have to determine optimal set of codes for the given message. You have to determine optimal set of codes for the given message. So here in the previous example, the codes that we have prepared ourselves are 0 and 1. there might be different codes that are possible. I can code A with a 1 and B with a 0. I can code A with a 00 and B with a 01. I can code A with a 00 and I can code B with 11. So now many number of feasible solutions are available. Which is an optimal solution? Which set of codes are optimal set of codes? That you have to determine by using greedy approach. And the objective function here is you are going to minimize the computing time. So if you have optimal set of codes, naturally the computing time or the message transmission time will be reduced. You have to minimize the transmission time. Now, what is the selection procedure? At each step, you are going to apply. At each step, you are going to select up smallest sized files for merging. So this Huffman coding is based on optimal merge patterns. That is why we are studying these two topics in sequence. First, I have presented you with optimal merge pattern. Now we are studying Huffman codes. Huffman codes are based upon optimal merge patterns concept. So whatever concept that we have applied in optimal merge patterns, the same you'll apply it here to generate Huffman codes. Now, optimal set of codes can be represented by a decode tree. Now, how to represent this decode tree? So this was our decode table. The same information can be represented in the form of a tree. Now you can see here leaf nodes are your characters, and left side child will have a 0 weight. A right child will always have a 1 weight. That will be the process of your Huffman coding. Now, we'll try to apply Huffman coding process, greedy approach, and we'll try to generate optimal codes. These are the characters in the message. 5 different characters are used in the message A, B, C, D, E. And this is the frequency of the characters in the message. A is repeated for 3 times, B is repeated for 5 times, and so on. Totally, there are 20 characters in the message. The total message length is 20. Now I will have to generate optimal codes. For that, I'm going to apply optimal merge pattern concept, greedy approach to generate optimal codes. So for that, first I'm going to take leaf nodes. Each leaf node will be a character along with its frequency. And you can see that the characters are ordered as per their frequency value. In ascending order, I have ordered them. Least frequency to the maximum frequency. Now you have come up with the leaf nodes. Now at any point of time to generate the decode tree, you are going to merge any 2 characters or any 2 messages. So the greedy choice that we have to make is we have to select the 2 characters, the 2 leaf nodes that have minimum frequency and merge them. So that's why I have selected E and A and I have performed a merge. So 2 plus 3 after merging, it will become 5. Now, this is the file that I have and remaining 3 are there. Among these, there is a file of size 5, 4, 5 and 6. There are 4 lists, 4 files. Now I have to select any 2 of them with the smallest frequency. For that, I'm going to select this, and I'm going to perform a merge whose value will be equal to 9. Now I have 3 sorted files. This one with value 9, then I have this one with value 5 and this with value 6. Now again, among these 3, I'm going to select the ones with the smallest size. So I'm going to perform merging on 5 and 6 and the value of the internal node will be 11. Now I am left out with only 2 and I'm going to merge them, and the value of the root node will be 20. Now once you have formed this decode tree, you are going to put weights to the links. Left child's links will have zeros. So left child links will be associated with the value 0. Right child links will be associated with the value of 1. Now your decode tree is full. It's completed. Now you'll generate the optimal codes from the tree. Now, what will be the optimal code for A? You travel like this. A ikkada undi. Now you travel from the root node to your character A to find the optimal code. That will be a 0, and a 1. Follow the path from the root node to the character A. And you try to take those weights along the path. Now for B, this is B. The optimal code will be take the path from the root node to the character B and take these values 1 and a 0. So as such, if you find out optimal codes for all the characters, these will be your optimal codes, and you can see that these are of variable lengths. The length of this optimal code is 3. The length of this optimal code is 2. So it's variable length encoding scheme. And this process is what is called as Huffman coding. Huffman coding using greedy approach to generate optimal codes for the given message. Okay, so you can use the same process to find out how many number of bits have to be transmitted for the message. As I said, the total message length is 20, in which 5 characters are used. This is the code that we have generated using Huffman coding scheme, and this is the frequency of each character. So A code is 001, its frequency is 3. That is, the message contains 3 A's, and the size of 3 A's will be 3 into 3, which is equal to 9. Now B characters code is 10. There are 5 B's in the message, so the transmission size will be 5 into 2, 10 bits. So perform sum of all this, you are going to get this 45. And we have applied this formula. QI, sum of products of QI and DI, where QI is the frequency of the character, DI is the code size. Now, along with the original message of 45 bits, you'll also have to send the encoding table, and the size of the encoding table is this part. This is your encoding table. So you have to send 5 characters, represent them using ASCII code. That will be 40 bits plus 5 different codes that you have generated, Huffman codes. The total length of this codes will be 3 plus 2 plus 2 plus 2 plus 3. Totally it is 12. So the total size of the encoding table will be 40 plus 12, which is 52 bits. So whenever a message has to be transmitted, the length of the transmission will be equal to the size of the encoding table plus the length of the encoded message, which is equal to 97 bits. If you are using Huffman coding, the given message will be transmitted using 97 bits, which is far better than using ASCII code, because if the same message of size 20 characters is transmitted using 8-bit ASCII code, then the transmission size would have been 160 bits. So instead of transmitting 160 bits, you are using Huffman code and you are transmitting the same message using 97 bits, which is very, very efficient way of transmission. And if you want to go for this efficient transmission of message, then you have to generate optimal codes using Huffman coding. How you are going to generate optimal codes? By applying